Welcome back to Unit 4 Kinetics, Lesson 4, video number 3. So we're going to change a little bit here, and we're going to talk about how reaction rate changes with temperature. So we know why it does it. Now we're going to be able to quantify that. So we've already mentioned activation energy. That is our E sub A. The units on that can either be in joules per mole or kilojoules per mole. And the person that came up with an equation that's used in chemistry called the Arrhenius equation is Svante Arrhenius. I just like that name, Svante. And he is looking at how temperature affects reaction rate, and he was able to quantify that. So it looks like a really scary equation, but it's not bad if we work through it. So K, that's our rate constant. So we're talking about reactant rates. Rate constant is equal to A times E to the negative E sub A over RT. Now, we're not going to use this equation. We're going to use another form of it. So after calculus is applied to this, then we can use this in another form. You do not need to memorize this equation. It will always be given to you. So A is a constant. And this is the fraction of collisions with proper orientation. So it's something that's given to you. E, we've already seen, this is the inverse natural log, or the inverse ln. E sub A is our activation energy. R, you saw in Chem 1 with PV equals nRT. Here's R and T again. So R is the universal gas constant, which comes in a lot of different forms. And T is our temperature, as always. So this relationship we can talk about using this little flow chart. If we increase temperature, so this number, which is in the bottom of this fraction, if we look at how an increase in temperature would affect E sub A over RT, it would decrease it. But since we're taking a negative of it, it would increase that. That would increase the E to the negative E sub A over RT, which would increase K, which increases rate. So the opposite, if we decrease rate, these would all change. So all this is showing is an increase in temperature increases the rate, a decrease in temperature decreases the rate, and we can mathematically prove it. So once we do a little bit of calculus and we make a couple assumptions, if we assume that E sub A and A do not vary with temperature, we can derive the following equation using calculus to determine the effects of temperature on reactant rates. Just take my word for it. I cannot explain how they go from one equation to another. At one time, I may have been able to do that. Mrs. Simpson might be able to do that in calculus, but we're just going to make a leap of faith. So here is the equation that we're going to use. Now, it may look a little intimidating, but we know what all of these things are. Ln is a natural log. So we're looking at two different K values. So we're comparing things that are at two different temperatures. So E sub A is our activation energy. R is going to be our universal gas constant. So T must be in Kelvin. So remember, degrees Celsius plus 273 is equal to Kelvin. R equals 8.314 joules per mole Kelvin. That is R with these units. And then E sub A, because we have joules here, must be in joules per mole. So let's look at an example problem. Here we have an equation. We're given a K value at 0 degrees Celsius. We're given an E sub A. We want to know what is K2 at 37 degrees Celsius. So we know if we increase the temperature, the K value should increase, so this number should go up. Let's look at this. So temperature must be in Kelvin, 0 degrees Celsius. Well, that's 273 Kelvin. 37 degrees Celsius is 310 Kelvin. The other thing we have to make sure of is our E sub A, which is in kilojoules. We have to change that to joules, so it's 88,000 joules. So now we just have to put in all of our values. We know what K1 is, but we're looking for K2. So the ln of K2 over 9.16 times 10 to the minus third is equal to E sub A, 88,000, divided by R, which is 8.314, times 1 over T1 minus 1 over T2. So if you remember back, we had log rules. We said if we have a log of a fraction, it's the log of the numerator minus the log of the denominator. So to simplify that, we have the ln of K2 minus the ln of 9.16 times 10 to the minus third is equal to, well, when we divide these two, we get 10,600 times, and if we do 273 reciprocal minus 310 reciprocal, we get 0.000437. So now we can simplify this even further. So the ln of K2 minus, if we take the ln of 0.00916, we get negative 4.69 is equal to 4.63. So we multiply these two numbers together. Simplifying this even further, ln of K2 plus 4.69 is equal to 4.63. And now, all we have to do is subtract 4.69 from both sides. So we get the ln of K2 is equal to negative 0.0600. And then we do the inverse natural log on both sides. So e to the ln of K2 is equal to e to the 0.0600. This cancels out, and we get K2 equal to 0.942. Whatever units we had up here on K, it's going to be the same unit down here, so seconds to negative 1. We said that if we increase temperature, our K value goes up. We just mathematically showed that. So we've gone from 0.00916 to 0.942.